Hello, my friends. Hello, my RF microwave design engineers, researchers, graduate students. Good morning, good afternoon, good day, wherever you are around the world. This is Dr. Mohamed Nezami with another video series on a new topic in the radio frequency and microwave circuit designs. You may recall that I have my own YouTube video channel, and we just finished a whole new series on the on the circulators, ferrite circulator designs using ANSYS HFSS. Previously, I covered many other topics. You can go back to these videos and watch them, and I hope you enjoy them, benefit from them. They're to the public knowledge, spreading the public knowledge, basically. Now, one of the things one of the videos that I talked about was a series on the KU and KA band, both the low noise block down converter and the buck converters as well. So one of the videos that I had was this video here. About a year ago, I did this, which talked about the design of KU band SATCOM low noise block down converter. And in that video, I covered basically the system design of the low noise block down converter, where we take the RF signal from the SATCOM flat panel or the parabolic dish, and we have a low noise amplifier, and then we filter the this incoming signal via a bandpass filter, which is a critical filter. And then we have the down converter and then the IF section. Likewise, we have the LO that meets with the incoming signal to produce the, sine X times sine Y and produce the IF intermediate frequency. So we have the LO phase lock loop section that takes something in the S band and multiply it times 4 and then filter it and then goes into the mixer. Now, today's this series, so here's the system. You're a system designer. You design this, and you basically how the process of designing this thing. You design this thing, and you're happy with the chain, with the budget link, and with all the. Of course, when you design it, you have in mind all of these components that we picked already. We selected from the manufacturers of semiconductor manufacturers. These chips are all selected. Some that you may design, which in my case, I designed this filter in here. This is the bandpass filter in here. And this is the LO filter, okay? And these filters were designed using, no, I don't need that. Were designed using the Genesis, P-side Genesis frequency synthesis tools, filter tools, bandpass filter tool. And the topology I picked was the hairpin filter. Okay, so this is a very critical filter, and I'll show you in a minute why that filter is critical. Likewise, there is a medium-size order LO filter that filtered the basically the LO signal. We need to make sure that the LO in here doesn't leak, especially when you go through 4 times multiplier. You need to band pass and narrow, only pre-select the LO single frequency. You don't want to select the lower or upper harmonics, okay? So now the importance of this filter in here, one of the critical components that we have is that when you're a system designer, you design this chain, and you may use this tool here, the system view tool, and you're probably happy with the, let's say, the RF, let me see, I didn't run this for a while. So, but let's say that you have designed this, and okay, well, let me rerun this again so that we have the slide that I want to talk about. So, okay, until this runs, let's talk further. Okay, so these filters, you design them, and you're happy with their performance, you got the filter artwork in microstrip, and you, of course, you would have selected already the substrate in that case. Now the next thing you want to do is you want to pass this over to the schematic and PCB designer, if it's not you. And what happens is that when we go the design tools, we basically have the schematics like this. And what we want to do, we want to put that filter in there as a symbol, and then we have a footprint for it. So, and then we have of course, the layout. And in this case, I did this for a client in the US. So here is this is the filter that, let me take this off. This is the front end RF filter right here, okay? And this is the LO filter right here, okay? And right now, this is the LMB section, basically. So what we want to do is that this filter here is very critical to the operation because, okay, here we go. So this had ran already. So at the time, of course, we picked the input signal was minus 80 dBm. And then the output signal in here, you can see it's at minus 22 dBm, okay? The DCP, which is the desired channel power. So the noise figure of this is basically right now, let's see, what is the noise figure? Oh, it's not drawn in here. Oh, here it is. It's 0.685 dB, which is cumulative noise figure. So you're happy with this. And you, of course, in this design, you have used the bandpass filter, an equivalent S parameter. You imported it from your filter design tool into here. So I've used the actual filter response that came from the electromagnetic simulator. Okay, so what we want to do is we want to make sure that this filter, these filters here, okay, and as well as the IF filters in here, we want to make sure that these filters have been preserved in the layout, okay? Meaning when we came to the layout here, when we did this filter, we had to add a whole bunch of stuff like vias, copper pour. We had to use some bins, some mirror sided to go into the mixer. We have used the transition from the 50 ohm line into the mixer pad. Same thing for the LO as well. You know, the LO signal, we came in here from the ×4 and we filtered and so forth. So, and the way we want to preserve this is that we have to go through a process called, which is what I want to talk about today, which is the post layout performance verification, okay? What we mean by this is that we as RF system designers design the system, pick the components, pass those on to, in my case, I did my own schematics. So I draw the schematics, like in this case, this is the schematics for the in OrCAD, have all these sections here, okay? So what we want to make sure of when we do this, and we come in here, for instance, and when we put the equivalent of these filters, like, let me go back to the LO section in here, LO down converter section, okay? So when I go in here, this is the LO, how I did the symbol, and this symbol has a footprint, okay? And that footprint, once we pass it to the PCB, we need to make sure that in the PCB now, it does not deteriorate. Like, for instance, this filter in here, when it was designed basically as simple, just basically isolated from everything. And now what we have to do, we have to take this, and the PCB designer will add all sort of things. Like I added a transition from the ×4 pad onto the 50 ohm line, and I added this copper pour in here with the proper, so that we have housing on this to shield it. Okay, I want to make sure that this section in here doesn't deteriorate. So how do we do this? This is a concept that is called the post layout RF performance verification or validation. Okay, and what that is basically, we have a BC board that is ready to go to the fabrication. It costs a lot of money. Like this board costs tens of thousands of dollars in cost of producing a first time BCB spin. And if there's any mistakes in the layout, that requires a new respin of the board, and that will require tremendous amount of money and time, and therefore it's very critical. So what we're going to do is we're going to come into an existing board, and this, you don't have to do this for your own design. I'm doing it here for my own design, and in fact, it should be another person that does it, because like software testing, you wouldn't want the guy that wrote the code to do the test procedure or to do the test cases for the software, because psychologically you wouldn't want to try to find if there are any troubles, because this is your work, you're in trouble. So if there's any of you out there that has a board that is very critical for fabrication and would like to do post layout checking before you go to the fab, you can send that to me. Okay, you can send me the source file if it's in Cadence or Altium, or you can send me any of the industrial standard files like you have here, Gerber or DXF or ODB++ or IPC 356. And then what I do is I will take that into, like I did for this board, into the advanced design system or the HFSS. The next sessions, we will, whatever we do here with ADS, I'm going to do it again in the in HFSS as well. So here is this board. I imported it into ADS. Okay, and what I'm going to do is I'm going to go in and chop off pieces of this board to do analysis on it in the RF signal processing. So what I do is we will, for instance, let's say that I want to cut this section at first that has both the LO filter here, and I'll show you in a minute how I imported this here. So, and then I go in here and EM tools, and I'm going to cookie cut this. So I'm going to cut this, and that's what I got, is that this section only. And now I want to run this section. So, but this is a lot of copper, okay? And of course, you can do, of course, this is a 3D board right now. So we've got all the vias in there. You can check all the vias in there are basically correct and have. So what I did here, this board that we talked about in the Cadence, it's an 8-layer board, okay? So, or a 10-layer board. This is okay, where a lot of the other layers are for DC and control signals. So what I did here is I imported only the top, and I'll show you in the this session or next sessions how we do this. Okay. So now let me just for right now ignore this and just close this. And so what happens is that next is that you gonna come in to this pieces and you're gonna run it separately. Okay, so like I do here, we have a port in here. I put a port in here, and I put another port in here. And what I'm going to do is I'm going to check the response of this filter in while the layout, while the artwork is preserved from the layout. So this is I cut off this section in here, okay, and you can choose any section you want, okay, include with it. So to do this, for instance, I go into the RF Pro. And so this is the board that I have. So let's do the substrate as this one. This is the bottom copper, and this is the top copper. And this board, by the way, was done using Rogers 4003. And then I ran it already. So let me just go to the results. And of course, this one here, you can see what I did. Top. okay, is that we have the pins on this are basically, let's see, let me go here and so let's do wire mesh. So this is the you can see the artwork of this filter. So we've got the copper, the top copper, and we've got the bottom, and we've got all the vias, okay, and then the substrate is there right now. So I'm going to put the substrate is shielded here. So okay, so now let's okay, so the inputs to this, you can check this and make sure that the inputs are right, put in correctly the ports. So basically the ports, if you look at the ports, port 1 is, you can see the positive sign in here and the negative sign is on the bottom. So that's what I do is I use, and likewise, if you go to the output, port 2, basically it's right there, okay? And the way this was done, of course, is that we do it right here. So the layer is done here, in here, and then the of course the substrate is this here, okay? So the substrate, what I did is that when I imported the files from Cadence, all I did is I took the top layer, the second layer, which is ground layer, okay, and the VS, okay, and that's all I did. And then, of course, the substrate stuff. So let's look at the response of this filter, for instance, and what we're going to do is look at the, okay, I need to run it again. So what I'm going to do is let's go back. Let's go back and there's one issue here that this here needs to be okay, so now let's do this. So we're gonna go out of Pro. And hopefully this doesn't take a lot of time because I thought I saved the results already. So now let's see the options. So we've got the frequency setting right. And so we're gonna run it. And I'm gonna stop the recording so that I'm gonna pause the recording until this is done. Okay, so several minutes, this thing have finished. Okay, so we're gonna go in here and then we're gonna go to the results and let's look at the S parameter file, the response of the filter. So this is S11, okay, and this is S12, and you can see here's the filter, okay, the filter response, okay, and it is a little bit different than the original filter designed, which is this one here, of course, because that was the frequency response in there was computed from the frequency synthesis, okay, where this one here is actually based on the actual geometry of the filter itself in the from the actual layout, okay? But it's acceptable, okay? And the difference is now what I did is that we can go back to the system design tool, the system view, and in there, what I did, for instance, here is I imported the response of that filter. And let's see, this is from RF Pro, which is the red. Okay, so this is RF Pro so that we can see it. So the response is a little bit different. Okay, so what seems to be is that it's broader and shifted upward, where the original synthesis was a little different. And of course, we have in here, we have a finite amount of a realistic amount of rejection because basically the in to out, the isolation is not as good as the frequency synthesis tool computed. Okay, so nevertheless, Now it's okay. The passband was preserved, but we can troubleshoot this and further analyze it. So you can see how powerful this method is. So now what we did was we verified this. Now let's go back to ADS and close this, and let's look at the other filter, the LO filter. So what I'm going to do is go back here, and I think I have done it. No, this is from the synthesis tool, which, okay, so we're going to go back to these two, the two filters. And what I want to do, I'm going to zoom in here, chop this off, and just look at the LO. Okay, so I'm going to come in here and just grab this and just grab the sections that belong to, okay, so now we have that. So we're going to go to EM, cookie cut this and cut it out. Okay, I'm going to take out this one here because we don't need it. Okay, so now what I got is I got this, I got ports on it. Okay, so it's 4 and 3. Okay, and this is, if you look at the 3D of this, it's preserved. All the vias are preserved. Okay. Now let's look at the want to make sure that the okay, so we don't have the bottom copper, so we're gonna come in. Okay, I think I know what it is. So let's look at the okay, so this is, we don't have this here, so let's do that. So we're gonna go to the second, to layer 2 and create a ground plane. First of all, why didn't delete this? So I'm going to delete that, but I'm going to go in here and create. Okay, this here, the second ground layer, it's all continuous, so it doesn't really matter. You can draw that yourself if it didn't come through. Okay. Okay, so now we're okay. So let's go 3. Okay, so now we've got all the vias are connecting the top to the ground one. Okay, so now we're ready. So this one should RF Pro. Okay, so we're gonna go in here, save it. And I'll show you in a minute how all of this is imported. Okay, so we've got that, and if we solid the substrate, it's in there. So let's go in, and first thing we want to do is make sure that the ports. Now, by the way, we could work everything that I did geometrically to cookie cut the pieces that I want to analyze. You could do it in based on nets. In the HFSS, in the coming sessions, I will do it based on basically the net. Okay, so where in this one here, basically I will do it just geometrically. I'm going to cut it, but we will show next sessions how automatically we can have the program, the CAD tool, just cookie cut around the areas that we want to analyze, because as you know, this takes a lot of computational resources. So we want to narrow as much as possible, but still fully capture the impact of the copper in there, so that we don't want to cookie cut and make it ideal. Okay, so let's go in here. We've got pins in here. We've got pin in here and pin in there. These are the pins that I created there. So we're going to take those. Let me erase this one, get rid of this one, because I always get confused about them. So I'm gonna, first thing we want to do is we want to make a reference plane. Okay, the reference plane is the second layer. Okay, and then I'm going to take these pins and bring them in here. Okay, so I have this here, and if you look at that, that's basically the input at the filter input, and the negative side is at the bottom. Okay, so you could check it and see that it is indeed at the bottom. You want to make sure that is correct. So we're going to go to options. You're going to run this between, let's say, 5 gigahertz to 15 gigahertz. Okay. So, and let's go back to options, and we want to make the simulator microwave, momentum microwave. Okay, for right now. Okay, so this is done, and I'm gonna run it, and let's see. Hopefully, this will not take very long time. Now, again, until this runs. So basically, what did we do? Again, I'm talking about the concept of RF post layout. Okay, post RF layout designs. So what we do is we have an existing layout that you as an RF designer did, or some AutoCAD or some PCB designer did. And what you want to make sure is that you want to take this board after it has been done and right before you send it to the fab house and check this board. You want to go to critical places, like in this case, I want to see the response of this filter. Did it really change? I know I designed it. I sent the librarian, the PCB librarian, the footprint. He had he imported that, and I want to make sure, make sure that it did not change the performance, especially like, for instance, this filter was designed only to here. This is about a 40 mil wide line, which is the this is Rogers 4003 20 mil. So the width of 50 ohm line is about 40 some mils. Okay, so like for instance, in here I added this here because I did the layout myself on this one. I added this so that I transition into the mixer, and like for the yellow filter as well, I added all these copper around it to basically shield it. So I want to make sure all of that works. Okay, and this is still running. Okay, so what we do is we take the so we go into the system and we identify the pieces of the subsystems that we need to perform post layout thing. So I, as a consultant, if your company has a board that exists, if the designer is still around, or he's gone, or he's a freelance independent contractor, you could send me the file, your CAD file, and after I understand what the board does, what all the functions are, I could go in, identify the critical areas of the board that are critical to the fab process that you would want to check. And the reason we check this is because, remember, every time you spin this board due to mistakes, it's hundreds, it could be hundreds of thousands of dollars, because you involve a lot of engineers, you involve managers, engineers, and the fab house, and the cost of fabrication, the cost of PCB assembly, and to put it all back together, to retest it. That's a lot of money. So I could come in as an outside consultant. You give me this board, I verify it for you. I will locate critical areas. I will use EM tools, HFSS, and ANSYS to make sure that there are no issues. If there are issues, then we can catch them early on and go back to the designers and say, look, your filter did not perform. We had the PCB designer added this, or added vias in here, or added copper pore in there, or added a 90-degree transition or a minor transition, and then something happens. So we could send him back the DXF file. By the way, the files that I work with, basically, any of the standard files that you, for instance, in here, you can export either Gerber file, DXF files, like in this case, or ODB++. ODB++ is very interesting one, because that's the one I work with. That's the one in a minute, I'll show you how I imported all that from Cadence into ADS. And eventually I will show you how we do it into ANSYS. Okay, ODB++ preserves the 3D dimensions, the stack layer. It brings in the stack layer information. So all you have to do is just edit it, just correct a few things in there. And then so it preserves all the vias, where the DXF file, all it is a 2D CAD that doesn't preserve the third dimension. So you have to recreate the vias yourself, redraw them again, because they're just circles. They're just 2D circles. Okay, so this is done. So we're going to go to the results in here. And let's see what the frequency response of this thing is. So got the return loss is really good. Nice. And okay, so this is the response. And it seems like it's a nice filter. Now I exported this again into system view, and let's look at that. Okay, so this is the LO, and you can see again we also have a shift in there. Let me just identify which. Well, okay, so let me make the axis x-axis. Let's make it into gigahertz so we can see it better. Okay, so the RF Pro 1 had shifted again upward. And this has to do probably with the substrate model between the ADS and the actual one. So, but it's still, though, it preserved where that bestband is. So let's go back to the front end filter, and the same thing on the front end filter. You can see that it's as if the dielectric constant is a little bit deviated from the actual. So in any case, so this is really good tools, like I showed you before. So I'm gonna, just to make the video short, we're gonna cut in here, and then I'll show you more next week. So basically what you do, you have an existing, you start out with your, this is the LMB that was designed at the system level, where we studied all the system aspects of this, basically budget link, and look at best bands, compression specs, and we have verified in this. And in this, usually there are subsystems in there that you design using microstrip, like in this case, the RF front-end filter and the LO filter and the IF filters. So what we do is we take those from a synthesizer, and then we make footprint for them, and then use them as schematics, as a block diagram. And here shows that this is just a filter that links to a footprint that you basically bring in from the CAD file to the BCB. At the BCB, of course, we do the layout. So, and so what we do next is we want to import this. Basically, we do, first of all, you do your layout in here. So what I'm going to do is you export this, like in this case, I export as an ODB, okay? And I don't want to run it right now because, oh, it did run. Oh, okay, it's going to run. But anyway, what you end up with a file. Okay, here it is. So you end up with this, and you want to make sure that you use compressed TGZ tar file, gzip. Okay, so okay, so what you end up with is you get basically this file here, which is a compressed file. And if you open this file, there's a whole bunch of stuff in there that preserves all the board material. So what we do next is we can come into the ADS, and you can come in here and you can import a design, you see. And of course, you can import really from Allegro board, this board here, you can import directly into here, this board here, which you see here, done in OrCAD or Allegro, it's the same. But in my case, I really didn't do it that way. So what I did is I wanted to do ODB ++. You could do that. So, and you have a directory format or this one. So we did this, and we browse to the location, and here is this. And in there, of course, you have a bunch of options, okay? The options that you're going to get, first of all, you have an option of create component folder. Yes, I want to do. So it brings in the layers. Okay, these are all the layers, the stack layer, okay? And in my case, of course, I don't want to bring in everything. I just want the top. Okay, so I'm going to go to the top. This is the top, so I click that one. Well, let me deselect all of them first. So I'm going to correct the top and then the ground, okay, and the dielectric one, okay. And also, one important thing is the drills. You want to make sure the drills are brought in. So let's see, where is that drill layer? Okay, here it is. Okay, you want to bring the drill file. So you okay these, and then of course you have the nets. You really want to bring in the nets, and I'll show you next week why. I mean, the next session on why you want to bring in the nets, and of course the components as well. These components are going to be brought in because you can actually physically you can use those in the simulations. Okay, and then of course the connectivity on this. So create the layer stack, you click that and you just do that and it will bring them in. So basically right now, let's just make sure that. And so, okay, this and connectivity in here. I really don't want it to bring that in. These are the net connections. So you click that and this is the layers, the stack layer. And right now what it did is it brought the top, it brought the ground. The substrate is set to a default, which is FR4, and my material is not really FR4. Okay, so what I'm going to do, I'm just going to go ahead. This is also wrong. This is 20 mil. Okay, and the dielectric material is not right really, but leave that. We're going to fix it later, so don't worry about that. So I'm okay. So it did that, and here it is. You can see that the here's the okay. Here it is. Okay, so we've got the board right here. Okay, so ignore the other stuff that is on there. So what I'm going to do is first thing I'm going to get rid of the schematic, the connections. So tools, set connectivity. I'm going to get rid of this. Okay, so right now what you have is this, and therefore I can go in and start cutting, cookie cutting like I showed you earlier. Okay, so this is it. So basically, again, this is Dr. Mohamed Nezami. We are going to continue on in the next session. Let me just show you what I'm going to do next. Is I'm going to come into one piece of critical information, which is this here. This is the MOSFET transistor in here, and this is the input-output, the output matching device. And this is here is a radial stub with a quarter wavelength high impedance line to bring in the positive DC supply. I want to analyze this actually, this piece here. So in the next session, I'm going to show you how you do that based on a net-based, actually, not cookie cutting that. So what I did is I already did that as an experiment. Here it is. I took this one, and then I did an experiment where this line here, I showed to myself that what if this line wasn't there? What happens? And what happens if I actually go ahead and added a second double order radial stub? And radial stubs, as you know, these are open quarter wave stub that basically represents short, because as you know, quarter wave transformer, if the load is open, it becomes short. So it's short at this point. It's RF short, not DC short, because the purpose of this is to pass the DC and RF in here, and none of this here will look like open to the RF, but for DC it will bring in DC. And that's basically this here. So we wanted to bring in the DC to the drain of the MOSFET, the low noise amplifier. But at the same time, look, this point here, from this inward, it look high impedance. And that's what I did here. So basically that's what we did. And so next week, I will show you the how you do that. So Okay, so I think I ran it already, but let me just give you a preview. So hopefully, if I save the simulations, let's see. Oh, okay, it was saved. Okay, so okay, good. So we'll talk about that in the next session. Okay. Well, this is Dr. Mohamed Nezami again, thanking you for the for attending this. Again, our topic today was the post PCB RF and microwave post layout performance validation or verification. And that's where we take an existing PCB that you did and import this into EM packages, electromagnetic simulation packages like ADS. In this case, I did, and I will do ANSYS in the next sessions, which that is, in my opinion, is a little bit more powerful even, because you can do more 3D simulations. Like you can actually see the impact of the shields of the lead on the shields, the height of the lead, and so forth. So we'll do that next. So so if you, I'm an independent contractor, and so what we did today, we verified two filters that are critical to the operation of the low noise amplifier that I did in this video here. You can go back to the video. About a year ago, I did this. So this was designing the system level, the system view. Okay. If you have a board that you want to outsource, either the design or the post layout, please reach out to me with this email here or this phone here. I operate out of Jordan, and I go back and forth to the US. And so if to my clients in the US, this is as if you are giving it to somebody in the US as far as financial processing and taxes and all of that. So it's transparent where physically I am. So I appreciate it. And if you have any questions, please do reach me at this number. Thank you very much. Until next sessions. So we're going to continue. We're going to have about several sessions on the topic of post layout validation and reverse engineering, you might say, reverse check a design, so that we can avoid having you to go through, send a file to the fab house and end up with spending a lot of unnecessarily money to do that. We can, for a few $1,000s, you send that board to me, and you can avoid having to pay hundreds of tens of thousands of dollars in fab and BCB and PCBA and testing and re-engineering, respinning, all of that. We can locate areas of the design where there might be an issue, and I can work with your designer and say, there's an issue here, please, can you go back and check this, verify this? We verified it for you using these tools, and this is what we got. Why are we why is this thing not performing? So before we send it to the fab house, we catch it, so that you don't find this on the bench and end up with hundreds and tens of thousands of dollars and months of time and labor work on this. So until next time, thank you very much. This is Dr. Mohamed Nezami. All the best of luck to you and everyone else. Thank you.